Hello, good day everyone. I hope all of you can hear me.
Hello, sir.
Hello. Okay, in the previous class, I think what we covered over here was that we developed gate logic and implemented it on relays, and we also proved it on the simulator, the Proteus that I also shared with you. I hope you would have downloaded it until now. Okay, one more thing. Have you visited the lab until now in the campus?
Excuse me, sir.
Yes.
You said what about lab?
I'm saying that if you have visited the lab at your campus until now.
No, it's been like a year. We haven't been in the lab, but we've been in it.
Okay, you have been there. All
Yeah.
right. So, okay. Is it all right if any one of you can go over there someday and get me on a video call on WhatsApp or in Teams also anywhere, and
Yeah, sure.
what are the things available over there? So uh,
Okay.
can
No problem.
try it again. Yeah, whatever we do in theory
Uh,
or whatever we do on Proteus, so that you can go and implement things over there.
all right.
Okay.
So within this week?
Yeah, within this week, whenever you are free.
Okay.
So I want to see what are the things available in your lab, what is the equipment there, what you can work on. Based on that, then I will give you some practicals to perform in the real time,
All right. Good.
Okay. All right, then let's go ahead with the lecture today. We finished our lecture last time at by implementing and OR operations on relay, and we moved on to optocouplers. Optocouplers, what are optocouplers? These are the devices. Okay, um, give me a sec. Okay, I hope you can hear me properly now. Uh, okay, we are talking about optocouplers here. Uh, the optocouplers basically are the devices which convert an electrical signal to light. Okay, this is what optocoupler do. It converts the electrical signal, whatever the electrical signal you provide at the input side, it will convert it into a light signal, okay, an opto signal. So how does it do that, and what is the purpose of using it? Okay, an optocoupler in a package, it is designed like this. Okay, this is a 4-pin IC integrated circuit. This is pin number 1, 2, 3, and 4. Usually an optocoupler comes in a 4-pin package. So inside the IC, there is literally an IR LED or any other LED. At the input side, you provide a signal to it. It translates that signal into a light, and on the basis of that signal, the transistor gets biased. Okay, you get a switching signal at the output side. One of the properties or one of the characteristics of the optocoupler is that it provides uh, isolation between input and output. Okay, as you can see, at the input side you have electrical signal, at the output side you have the electrical signal as well, but you can isolate the input side. Supply is attached to it. Let's suppose not power supply, you can say a microcontroller or a PC is connected. At the output side, some other circuit is connected with another power supply. It can still work. There is no need to attach anything from output towards input. Okay, for example, let me give you one of the examples here. We have a power supply here. Okay. At the input side, as you can see, I have attached power supply of 5 volts and attached it to a switch named as S1. So in order to turn on the optocoupler or turn on this LED inside it, we need to press S1. Once I press S1, the optocoupler will be turned on. At the output side, you have a transistor over here. At the output side, there is no base. Literally, there is no base because the base is basically, you can say, is a photodetector. Or you can call it, in a package, you can call it a phototransistor. So basically, it detects the light and turns on the connection between the collector and emitter. Okay. We were talking about how the switching will occur over here and how to connect the output circuit. Let's suppose you have a DC motor attached to this transistor. Uh, okay, my stylus is not working, so can you give me 1 minute so I can charge it?
Oh, no problem.
Just give me 1 minute. Yeah, until then we can talk about the optocouplers. The basic idea is that it provides an isolation between input and output. So the input and output are not connected to each other. The same thing goes for relays as well. If you remember the symbol of the relay, okay. If you remember the symbol of the relay, here you can see at the input side, there are two switches connected to it, to the coil, and the coil and the output are literally. So how was the switching occurring over here? The switching was occurring due to the electromechanical you can say the electromechanical phenomena. Once you provide the signal at the input side, the coil is energized, and due to that, the bar at the output side, it goes from normally closed to normally open, right? So input has no relationship with the output electrically. Similarly, in optocouplers also, uh, there is no electrical connection between the input and output. In order to translate from lower input to higher output, wherever there is a necessity of that, then you can use the diode. Let's suppose if you are running a DC motor of 24 volts with a microcontroller or an Arduino, then you cannot do that. Okay, in order to do that, you need to translate that 5-volt signal from the microcontroller to 24 volts. So in order to do that, you need to attach either optocoupler or a relay. Uh, you cannot attach a relay with a motor if you are controlling its speed, because controlling the speed requires a PWM signal, not in high or low logic. Okay, so when you uh, provide a PWM for a motor, then you need to attach a optocoupler over there. Uh, so it can work on, or it can switch on high frequencies as well. I hope you can understand the idea. Okay, let's see.
The output of the optocoupler
Yeah,
is, you said it converts signal to light, right?
yeah.
So the output is light.
The output of LED is light, but again, it translates that light signal to electrical. So at pin number 4 and pin number 3, you will be getting an electrical signal, okay, in form of something like electrical signal.
Okay.
Okay. Over here, you can see that we are using transistor as a switch. Okay, so once at the base, usually transistor works like that. When a certain voltage is provided at the it switches. It switches in such a way that collector and emitter, they are switched. Okay, I'll give you one example. Uh, I hope my stylus is working now. Okay. Okay, let's suppose this is a switch, and this is your okay, still not working. This is your collector, and this is your emitter of the transistor. Okay. Uh, so in order to turn this on, the transistor, you need to provide some voltage, that is 0.7 volts at the base. So the collector and emitters are shorted together. Okay. The same thing happens over here as well. Instead of providing electrical voltages at the base, uh, this is actually a phototransistor, so it detects photons from the LED. So these photons basically do that part, this part, 0.7 volts. So they basically turn on this transistor, shorting collector and emitter. Okay. So if you are attaching any load to it, you can attach load at pin number 4 and pin number 3. So let's suppose I'm attaching a relay over here, or let's do a relay first, and then we'll see again. Okay. We attach plus 12 volts over here. And let me attach a relay. So over here, this is your common terminal, normally closed and normally open. Let's suppose at the output side of the relay, you're attaching a bulb, a 12-volt bulb, okay, and the common will be connected with, okay. Okay. So what I have done over here is that I've attached a relay, and with the relay at the output side, I've attached an AC uh, supply and attached it to a bulb. Okay, this is a bulb, and this is a 220-volt AC supply. Okay, so what happens now? When I press this S1, uh, the circuit will be completed at the input side, and the LED inside the package will glow and turn on this transistor. Okay, when it turns on, the collector and emitter are shorted together, so at the emitter output you will be getting 12 volts over here. Okay, so once the circuit is complete, the current will be passing from the coil towards the ground. At that time, the coil will be energized, and the bar connected to normally closed will move to normally open. Okay, once this happens, uh, the AC circuit is also completed, and then the bulb at 220 volt will be, turned on. Okay, so this is one of the examples of using optocoupler. And what is the advantage? The advantage is that we can translate uh, lower voltage input or lower current input to a higher one. Okay, I hope you can get the idea of it. One more thing that we can do over here is that we can attach a motor, and we can also control its speed, because we are dealing with transistor over here. It can switch at high frequencies, but uh, if we attach a relay with a motor, it can only turn on or turn off the motor, but cannot control the speed, because it's an electromechanical switch over here. I'm talking about this switch. Uh, my stylus turned off again. There is some problem here. I'm talking about uh, the switch over here. Okay, I'm talking about this switch. That this is an electromechanical switch, so it cannot turn on and turn off at high frequencies. Maybe it can turn on 10 times in 1 second, but it cannot turn on and turn off in 1000 times in 1 second. Okay, but optocoupler can. The frequency of optocoupler can go to tens of kilohertz. It can go to megahertz as well. So when you attach a motor to it, and the frequency is quite high, the speed is the movement of the motor is quite smooth. There is no jerking. But when you attach a motor, a DC motor with a relay, you will observe that when you turn it on or turn it off to gain or change the speed, there will be a jerking involved over there. Okay, I hope you understand the idea.
Sir, I understand, but not 100%. So I have a question.
Mhm.
You said we cannot use relays to control the speed of motor, right?
Yes.
And you explained why, but I didn't quite get it.
Okay, let me explain it once again.
Okay.
All right. Okay. As I told you that optocouplers can run on high frequencies because we are dealing with transistors and they can switch at high frequencies. So we can use them to control the speed of the motor. But when we are talking about the relays, this switch is basically an electromechanical switch. Okay, let me write it. Electromechanical switch. Okay.
Yeah.
Yeah. It means that there is a metallic bar inside the relay, and this is actually a metallic bar. Okay.
Okay.
So it has a certain speed. You cannot turn it on and turn it off at very high rate. Maybe you can turn it on and turn it off 10 times in 1 second, but you cannot turn it on and turn it off 1000 times in 1 second because it is a physical relay. That's why.
Mm.
When we talk about transistor and optocoupler, uh, it is a solid state device. Okay, so by using a solid state device, you can reach very high frequencies. That is the reason that I said that you cannot control the speed of DC motors, especially with the relay. I hope you understand now.
Yeah, I totally understand it. And so if we test it, if we try to use it, when we
Yeah.
try to change the speed, so maybe the motor will react. I mean, there will be lacking in when it reacts. Some, for example, it will be very fast and then slow. Would that
You
happen?
are talking about relay.
Yeah. Or we cannot use
Okay.
it at all.
You can use it. What happens that when you start switching at high frequencies, what will happen that the relay will be stuck to
Uh,
one of the terminals. It cannot go back until you disconnect it. So this
yeah.
is what will happen.
Yeah, because I've used it. I faced something like that. There was sound in the relay and like quite stuck, something like that.
Yeah.
Yeah.
So this is the reason that you cannot provide a PWM signal to a relay. Uh, I hope you know that what is PWM. Let me give you the idea. PWM is basically pulse width modulation. Okay, it is actually a stream of uh, zeros and ones. So this is actually a signal. For some time the signal is zero. For some time the signal is 1, 0, 1, 0, 1. So this is a stream going towards the motor, or you can say this is a PWM signal. So 0 means 0 volt here, and 1 means 5 volts. Okay. So let's suppose if time to remain high is 50% and time to remain off is 50%, then the motor speed will be 50% because the average voltage that you will get at the PWM output would be 2.5 volts. Okay, because off time is also 50% and on time is also 50%. That's why you will be getting half voltage. Due to that reason, the speed of the motor will be halved. Okay. So when you provide this type of signal in low frequency, there will be you will observe jerking at the motor. Okay. If you increase the frequency of it, I mean that this signal, this overall signal repeats itself 1000 times in 1 second. You can imagine that how much faster the switching will be. So when you provide this type of signal, which is switching at this rate 1000 times, that is 1 kilohertz, then the speed of the motor will be quite smoother. Okay, so what we were talking about here was that if you provide a PWM signal at the relay, what will happen? At low frequencies, the relay will switch on and switch off. Okay, but that is quite an annoying sound. And second thing, what will happen is that when you increase the frequency or when you increase the speed of the motor, what will happen is that the one of the terminals will be the bar will be stuck to one of the terminals, maybe to normally open or maybe to normally close. It will be completely off or it will be completely on. Okay, so instead of attaching a motor with a relay, what we do is that we attach the motor directly to the optocoupler, or if it is a high rated motor, I mean that if it consumes a lot of power or it consumes a lot of current, what we can do is that we derive a power transistor with optocoupler and derive the motor from that transistor, that power transistor. Okay. Uh, Hence, I think that I have been able to make my point over here that in order to run the motor over here, a DC motor over here, you will need to attach a motor directly to optocoupler if it is a small one, or if it is a little bit larger one, maybe it consumes 1 ampere of current or 2 amperes of current, then you will need to attach a power transistor here. A power transistor where at the output of the optocoupler. Okay. We will see one example also over here how we can do that. Let's do it. Okay. Okay. So this is our optocoupler running at 5 volts. What happens when we press S1 is that it switches the collector and emitter. Okay. Now, what I will do over here is that connect a 5 volt supply to the collector and connect another transistor. This is the power transistor. Okay, and attach the emitter to the ground. This resistance over here is basically a pull down resistor. Okay. In technical terms, what it will do, it will make sure that when your optocoupler is providing nothing over here, 0 volt, I mean that the transistor is not turned on, this pull down resistor will make sure that at your base 0 volt is going. Okay, so this will make sure that in any case your transistor is not turned on. Okay, until and unless the optocoupler turns on and turns on the transistor inside it. Okay, let's connect a motor to it. So here I have attached the motor with this transistor, and where I have attached it as the collector. Okay, so uh, there is one thing a little bit odd over here is this diode. I've attached this diode in a reverse position, and why is that? Uh, why I have attached it? There is a reason behind it. I'll come to that later on. But just let us see the working of this circuit. At the input side, I have attached S1 with optocouplers input. So once I press S1, what will happen is that uh, optocoupler will turn on this transistor inside it, and the current will be passing from it towards the other transistor. Once it happens, logic high input will be given to the transistor outside, and what it will do, it will saturate this transistor. Once the transistor is in saturation region, or you can say it is turned on, uh, then the circuit at the output will be completed, and the current will be passing from the load, that is motor, through the transistor and towards the ground. Okay, so your motor will start running in one direction. All right. Uh, let's suppose at the input side, I do not attach S1, but instead of it, I'm attaching some microcontroller pin, or let's say an Arduino pin, which is giving a high frequency PWM. Sorry, is providing high frequency PWM at the input terminal. Okay. So what will be happening over here? For this amount of time, this transistor will be off, and this transistor will be off also, and the motor will be off also. But uh, sorry, for this amount of time, and for this amount of time, the transistor will be on. Okay. So half of, let's suppose the duty cycle is 50%. Duty cycle is 50%. So it means that 50% of the time the transistor is off, and for the 50% of time the transistor is on. So which means that the motor is actually running at 50% of its maximum speed. Okay. So if I want to increase the motor speed, what I will do over here is that increase this time. Okay, time to remain high will be increased, and time to remain low will be decreased. What will happen over here is that when we increase the time to remain high, the transistor will be switched on for a little bit uh, longer period, and it will be turned off for smaller period. Okay, for a smaller duration. So in that case, let's suppose the time to remain high is 75%, and time to remain off is 25%. So and that means that the motor is actually running at 75% of its maximum speed. Okay. Uh, in the first case, when the motor is running at half speed, it will be okay, running at 6 volts, and when it is running at 75% of its maximum speed, it will be running at almost approximately 9 volts. Okay. Uh, When you provide 5 volts at the input, I mean that time to remain high goes to 100%, then the motor will be running at its maximum speed. Okay. I hope you understand the concept over here. Okay, one more thing that I wanted to clarify over here, the working of the diode at this position, at the collector's transistors collector. So why we have attached it over here? The reason behind is that when the motor runs, it provides back EMF to the circuit. Okay, this is the extra voltage generated by the motor itself. When it happens, it is actually very dangerous for this transistor. It is actually very difficult, or it is very dangerous for this transistor when motor generates a back EMF. Okay, back EMF. Because motor is actually an inductive load, the reason is that whenever you provide the power to an inductive load, it creates some electromotive force inside it, and which can also damage your transistor or your uh, back circuit. If your if this transistor fails, it can also affect the optocoupler. Okay, so this is one of the main reasons why we use optocouplers instead of attaching directly the Arduino to this transistor. Okay, it provides safety. This provides safety to your computer, or you can say the back circuit. Okay, how it is providing the safety? The reason is this isolation. Okay, even there is a back EMF from the motor, it will burn this transistor, it may burn this optocoupler, but it cannot go back towards the Arduino. Okay, or PWM generating equipment. I hope you understand the whole picture, whole idea. Okay, one more thing, what happens to the back EMF over here? The back EMF that is generated by the motor, it actually goes into this loop, and it loses its energy in a certain time period, but it does not comes back towards the transistor. Okay, it does not do that. So is there any confusion until now? Any questions?
Sir,
Yeah.
you said the motor has some back EMF, which is bad for that circuit,
Yes.
and and is that also the reason that we use the reverse diode?
Yeah. This is the actual reason why we use the diode in reverse.
I lost your voice, sir. Can you repeat it, please?
Yeah, this is the actual reason that that is the reason that why we use the diode in uh, you know not in forward bias but in reverse bias.
And if let's assume we don't have that problem of back EMF, would we need diode?
No, then no.
Oh, okay.
Okay. Have you worked with relays? The industrial
Uh,
relay?
one time we created a project, we worked with it. The yani
Okay.
one time.
All right. If you have used an industrial relay, there is a small LED inside it. If you would have noticed that. That is small LED because relay is also an inductive load. It also generates, it is a coil basically. You provide a signal to the coil, it induces EMF. It also sends the back EMF to the circuit. So there is a diode inside it. Usually it is there, but in most cases it is not there also. So you will have to attach it, the diode, in a reverse bias way. Okay. So sorry. Okay. So I was talking about the LED inside the relay. That LED basically tackles that back EMF. So whenever you are dealing with an inductive load, then you need to attach a diode in a reverse biased way. Okay. If you are using a resistive load, then no problem. I hope you understand what I have just defined.
Yeah, clear, sir.
Okay, clear. Any other questions until now?
I don't have any questions.
Okay. All right.
But I lost your screen. If you're sharing.
Okay, you are unable to see it. Okay. I hope you can see now. Yep.
Yeah, no, I can see.
Okay, good. Okay. Uh, have you ever worked with any sensors before, like LDR or any other sensor?
Yes, we have worked with some of them.
Okay, you have worked with several of them. All right. Have you practically worked with LDR before?
With LDR,
Yeah.
I don't remember. I know. I don't think so. No.
Yeah, okay, okay. All right. Let's do one of the scenarios. Uh, if you would have noticed on your streets that there are some street lights, okay? These street lights basically they turn on whenever there is evening. When the sun is setting, they automatically turn on, and whenever the sun rises up, they automatically turn off. Okay, so there is no one, there is no person sitting at any place or in a control room that is switching those lights on or off. So how uh, the whole system is working? So let's look into that. LDR is actually a sensor which uh, abbreviates to light sorry, this is not detection, it is light dependent. Light dependent resistor. This is actually a sensor, and it is a 2-pin sensor, and the 2-pin sensor works in a way that when light is reflected on the surface of this resistor, the value of the resistor changes. Okay, I hope you already know how a variable resistor works. This is a symbol of variable resistor, and this is a symbol of LDR. Okay, for variable resistor, you are required to change the resistance mechanically by rotating the potentiometer, right? In LDR, what happens is that when there is a light reflecting on the surface of LDR, the resistance changes. Now, this phenomena can be both ways. Like if light is reflecting on it, the resistance may increase or it may decrease. Okay, depending on the property of that material, right? Let's suppose in normal condition, when there is no light, and the resistance of the LDR is maybe 5K, and when we start exposing the LDR with light, it can be any light, its resistance rapidly changes towards this maximum point. That can be around 50K. Okay, it can be vice versa as well. Vice versa means that it can be opposite as well. When light is reflecting, it may decrease from the maximum point, or it may increase from the minimum point. Okay, so whatever it is, the basic concept is that when light is reflected on a surface of the sensor, the resistance changes. Okay, so how we work this LDR to turn on a street light? Let's have a look at it. Okay. Okay, another symbol for LDR is like this. Okay, so don't worry about it. You can represent LDR like that, or you can represent LDR in this way as well. Resistor. Okay, any of these. So let's complete the circuit. Okay. This is one of the example circuits you can make for street light lamp. So where is the street light lamp? This is your street light lamp. Okay, you attach it with a 220-volt AC supply. Okay, and how we have connected? We have connected with a relay. So this is your relay. Okay. What we have done over here at the input side, I attached an LDR. This is your LDR and attach it with a 4.7K resistor, and we have made a voltage divider over here. Okay, so what happens over here is that at certain resistance, when a certain amount of light is the sensor is exposed to certain amount of light, set amount of light, what happens is that it turns on this transistor, and once this happens, the current will be passing from this coil, okay, towards the ground, and in action, this bar, the electromechanical bar, will move from normally closed to normally open by completing the circuit of it, okay, and it will turn on the street lamp. So what will happen? We can actually tune this input over here by making this resistance variable. Okay, this resistor over here is also variable, and the other resistance, let's say R1, is also variable. Okay, we can change the sensitivity of the circuit. We can change it in such a manner that when there is a sunrise, the transistor will be switched off. Okay, and when there is a sunset, the transistor will be switched on. Okay, so we can change this sensitivity by changing this resistance over here. Okay, so do you understand the idea over here?
Yes, sir. And
Okay,
when the resistor is on, then the 12 volt will be connected to the ground, right?
the 12 will be connected to the relay.
Okay.
You can say that the transistor will be switched on. In that case, the current will be passing from the relay.
And when the transistor is off, so there will be no voltage around the circuit, right?
Yeah, at the output side there will be no voltage. This transistor will disconnect this path, and
Yeah.
the bar will go from normally open to normally closed, back to its original position. So I hope you understand the concept of using LDR, and this is one of the scenarios that you can actually test in your labs as well. Okay, if LDR is available in your lab, then you can test it. Okay, one more thing, if you are testing this circuit, do not forget this diode. And do not forget it to connect it in a reverse way, otherwise there will be a problem. Okay, if you attach it in a forward bias way, then within one switching, your transistor will be burnt. Okay, so make sure that you connect the diode in a correct way. All right. Okay, I think that is enough for lecture today, and let's try to implement this circuit over here The optocoupler, the basic one that we developed, the first one that we discussed in this class. Let's implement it on the Proteus. So give me a minute to just switch the screens. Okay. All right. So I guess that you all have installed this software, the Proteus that I shared with you already in Teams. If not, then kindly install it so you may perform some practicals virtually uh, in order to verify your theory. Afterwards, then you can implement some of those practicals in your lab in real time. Okay, so okay, what we want to pick over here is that we want to pick a relay. So we take an animated two-pole relay over here so we can see when it switches. Okay, we already have an LED. We can add a transistor. Okay. Don't have them. We have a transistor here. Okay. All right, no problem. hopefully we can so here it is, an optocoupler. Here you can see inside the package there is a diode over here. This diode is basically an LED, and the transistor is being run or turned on by this LED. Okay, so just over here we attach a switch and attach a resistor. Okay, ground it. Okay, all right. At the output side, what we are going to do, we are going to turn on the relay. Okay, so we attach a battery here. Right, and connect this ground over here. Okay, so what happens when I turn on this LED? Oh, sorry, switch S1. Okay, it's not working. The reason is that I have provided 1.5 volts over here. The relay is basically working on 12 volts. So until unless we provide 12 volts over here, it will not work. Let's see it works again or not. Okay. Cannot turn on. Let's make it 5 volts and let's see if we can turn it on or not. Okay, here you can see it did turn on from normally close to normally open, but there is some error with the simulation. We are having some issues over here, so I'm not sure what is the issue. Okay, what we can do over here right now is that we can attach one LED. We can rotate it. Attach it over here. Let's see what happens. Okay, I'm having some of the issues. I'm not sure what are the issues. Okay, let us take another optocoupler. I'm not sure what is the problem here, but it should be working.
Okay.
The reason may be because I'm working with a correct version of it.
And maybe.
Yeah, the reason maybe it can be possible. So doesn't turn on. Okay. Okay, voltage is going over there, but I don't see anything. Okay, here you can see it is working properly over here. Uh, the LED might have been a reason for it, because the LED cannot work on 12 volts. It works on some 1.5 volts or 3 volts. So instead of LED, what we can do is we can attach a diode here. For simulator purposes, there is no reason to attach a diode over here. We can work without it also. So let's attach output bulb for it or something like that. Let's see what we can do over here. Do we have a bulb? A lamp. Okay, we have an animated lamp, and this lamp can be connect a lamp over here, and attach it to normally open here, and we can take, okay, we have an animated lamp, and this lamp can be, connect a lamp over here, and attach it to normally open here, and we can take, we attach a sinusoidal source, and let's see how it works. Does it work or not? Doesn't work. Maybe we are putting wrong value here. Okay, one more thing. Here I saw it right now. Here it is 12 volts. So it doesn't work either way. Okay, here you can see now.
Now it's working.
Once I press S1, it switches on the bulb. Okay, and once we turn it off, it turns off. Okay, now instead of a switch, we can also attach any type of sensor here. Like the sensor that we discussed earlier, that we can attach it over here, an LDR. Uh, let's see if do we have an LDR over here so we can work on it. Okay, we have it. Okay, I'm sorry. I turned off my mic before because there's a prayer time over here. So what I'm doing right now over here that instead of using an LDR, actual LDR in the software, uh, we are using a potentiometer, a variable resistor. The reason is that actually the LDR itself requires physical light to vary its resistance, which I'm not sure how to do it on this software. But instead of it, what we can do is that we can attach a variable resistor over here instead of LDR and work it as an LDR. All right. So let's see when we can turn on this resistance. So, see, when I changed the resistance value to 500 ohms, the LED at the output turned on. Okay, let me change it back to 50K and see the result. Now you can see the LED is dimmed, right? So what I can do over here, I can, in order to turn it totally off, maybe decrease this resistance. Now you can see the LED is completely turned off. So what I have achieved over here is that this sensor, this variable resistor, this is for the sensitivity for setting the LDR, and this is a sensor. Okay, when there is no light, the resistance is maximum. Okay, 50K. Whenever there is light, the resistance it reduces to its minimum level. So let's suppose we check it again, change it to 500 ohms and try to run it. Okay, so when the resistance is set to 500 ohms, the LDR resistance, you can see at the output LED is turned on. Right now, for your practice, you can develop the circuit. What I want you to do is that attach the circuit over here, this circuit, this whole circuit, integrate this whole circuit with this transistor. Instead of using this switch, what I want you to do is that I want to switch this bulb at the output bulb from this transistor switching. Do you understand what I'm telling you?
Can you repeat that?
Okay. What I want you to do right now, not now, I mean that after the class, this is the output circuit, right? From optocoupler to the relay. What I want you to do is that instead of using this switch, instead of using this one, what I want you to do is that detach it and attach this whole circuit with this transistor. I want you to derive this PC817 optocoupler using this transistor. And what I want is that I want you to control the switching of the light using this LDR. Did you understand now?
So we only remove the switch, the button, or I mean
Yes.
it's whole circuit. The
No,
battery
not
one.
the whole circuit. You can attach another battery, whatever you want to do. What I want you to do right now is that just delete this object. Okay.
Yeah.
Okay. Now this is the pin available to you. Now I want you to attach this whole circuit now to this transistor. So when there is a light, it will turn on this lamp. Okay. When there is no light over here and the resistance increases to 50K, this relay will be switched off. Okay.
So you mean when LED yellow D1 is turned on, we have to turn on the light bulb too.
Yes. Turn on the
Okay.
light bulb using this optocoupler.
Yeah.
Okay. Understood?
Yes.
Okay. Great. So I hope that all of you have understood that what you have to do in your free time. Once you complete this task, you can implement some of it in your lab as well. I'm not sure what type of equipment is there, but in this week, one of you guys go to the campus and show me what are the things available. So we can.
So yeah, what time works for you? Because you said do a video call. I can see.
Okay. What time will be feasible for you? Which day will be feasible for you to go there?
Uh, mm, Monday, Wednesday, Thursday, Friday. Friday, no. Yeah, Monday.
Okay. Monday means
Wednesday
tomorrow.
means tomorrow. Yeah.
Okay. What time?
Um, what time? Let me check. I can my table tomorrow. Maybe from 2 to 3.
2 to 3. All right. We
1
have a
to.
class tomorrow at 3 o'clock.
Yeah, we have a class at 3.
Okay. So you
My
will be
house
in
is very
campus
close to the
while.
university.
Oh, okay. Okay.
Yeah.
Understood. Okay. Then just before the class, we can discuss about the items or equipment available in the lab. Maybe at 2 o'clock, you can call me on WhatsApp. I will be
Yeah.
available.
Yeah. Okay.
Okay. So what we will do afterwards, once we verify what are the equipments available to you to work on with your hands-on, then we can modify our experiments while which we are discussing in the class. Okay.
Okay.
Okay. I think that's it for today. So you do the task that I gave you right now as your assignment or whatever you can say. I will just check it tomorrow. You can share your screen and try to run it so I can see that you have completed or not, you have understood it or not. Whatever we are discussing in the class, what we are making in the class at your home, just try to simulate it. Okay, so you can remember things. So that's it for today. I think we can terminate our call. We can end our class now, right?
Okay.
Thank you very much, everyone, and hope to see you tomorrow. All right. Bye-bye.
Okay.
Okay.
Thank
Thank
you.
you. Bye.